Okay, looks like I'm recording. Yeah, I'm recording, okay. So let me explain this one more time. So when we're dealing with motion and forces, as long as you have no movement off the surface, so say for example, you have, oh no, what happens? There we go, great. Say for example, you have something flat and a block on there, and the block's not going off, the surface are off the table. As long as it's flat, you can use that formula where W equals mg, and g is negative 9.8, as we know, because g is always going down, acceleration due to gravity. If it's sloped, remember Fn is this. For flat, that's Fn, and weight's that. But for sloped, Fn is still perpendicular to the surface, but W is now this. Then you have to set Fn equal to W sub y, where W sub y is W times cosine theta. So these are things you could always just go with and assume. They're not going to fail you. That's what you want to do, at least as a first step, to kind of know what the normal force is going to be. So like normal force could equal mg for flat, or it's going to be mg times cosine theta for sloped or angled surfaces. Then for your second step, draw a 3x diagram for parallel, for forces. Let me rephrase that. No, don't clear. Okay. For forces parallel to the surface. And what's going to happen, so generally speaking, let's say you have something like this here. Say I call this like FA, and I call this FB, and say the net force is to the right. So we're moving to the right. Then you're going to say F net is simply FB minus FA. And F net also equals mass times acceleration. And that's where you can kind of generalize it. Now, in the case of the snowboarder we just did for number 11, both your forces were going against your F net. Why do I keep doing that? In the case of snowboarder, his weight in the x direction and his force due to friction, but we knew that we had to go in this direction. And so that's why F net had equaled negative Wx minus Fk. And then of course F net was ma, then I just went through the motion and started solving it. So the free body diagram is actually essential. It really, really is that important. So that's why if no two situations are 100% identical, you really have to understand physically where the force is acting. Wx, by the way, equals mg times sine theta. And that can be, it could help you or it could hurt you, depends on where your motion is. But remember this, the snowboard is going uphill, so the motion is going uphill. So we want that to be the positive direction. So it means Wx and Fk were negative in number 11. Fk usually is going to be negative because it's going to be working against you. So that's a general way you can look at this. So let's keep this in mind as we do the lab. So now we're going to talk about the lab. And I'll keep the recording on because I think that's a good idea. Any questions about what I just discussed here? And feel free to take a picture of this too. Actually, let me do a screen capture of all this. Jeez, come on. There we go. Okay. And ultimately, you may have to wind up doing some kinematic equations later on. Once you get to acceleration, they want some other stuff you have to find. Then you do that later on. But I mean, hopefully, but you know, this is at least to guess the acceleration. Okay. So now we pull up the lab. So I'm gonna share my screen again. And actually I could clear, no, that's just that. Let me pull up the laboratory. Okay, we're gonna pull week 2 virtual lab friction. I'm gonna walk you guys through the first page. And then I'll let you guys kind of try some stuff on your own. Maybe I might have to walk you through the page 2 as well. Let's see. Okay, I'm gonna open it up. Click on it. Sure, keep it. Okay. So let's kind of just take a look at what's happening here. It looks like there's a guy, there's a box, FN's pointing up, parallel, perpendicular to the surface, FG is going to the center of the Earth. There's an angle. Just to keep things simple, let's actually not have any angle at all. And let's say we, whoa, okay, it was crazy. The small crate weighs 100 kilograms, as we're told, okay. Whoa. Okay, I'm trying to get the box. Hold on, I'm trying to figure this out here. Give me 1 sec. Okay, let's do this. Maybe we could probably move something heavier or lighter. Let's try to move a refrigerator. Okay, kind of funny. Anyway, let's look at the lab telling us to do. We can keep playing with this, but all right, what's the lab telling us to do here? So click Run Now, click on the Force Graphs tab. Okay, so let's actually do that. Force Graphs, okay, perfect. And then the next thing is set the ramp angle 0 degrees, okay. So set it to 0 degrees. So lower it. Okay, so it says 0 degrees right there. Okay, then check the checkbox would apply force and the force at the bottom left, okay. So applied and that, okay. We're going to examine the way friction behaves when you push an object on a flat surface, fine. You can make the wooden stick figure doll apply force to the crate by clicking on the crate and dragging along, or just slide the apply force slider up or down, okay? So if we look at this guy again, you could, we kind of see that there's something happening down here. Let me go ahead and clear all this for now, okay? Now let's look at the next part. Starting with the crate stationary, slowly increase applied force on the crate without having the crate move yet. What is the acceleration? How does the frictional force compare to the applied force? Okay. So we could slowly start increasing this. So let's say I make that 1. So it hasn't moved yet. No, right? Let's say I make that 2. Still hasn't moved. Let's say I make it 10. We still haven't moved yet. Say I make it 20. Pushing a little harder. Say I make it 50. or 250 actually. Say make it 500. Now it's moving. It's going to crash in. So you guys are going to play with this a little bit. I think that's the one thing that's going to be kind of neat here. So you're going to answer some of these questions here. What is the acceleration? Obviously 0 when it's not moving. Actually, hold on 1 second. Sorry, I closed this Amazon dropping off the package, so my bad. Yeah, so obviously acceleration is 0 when it's not moving. And the friction force and applied force are equal to each other, but in opposite directions. So that's kind of like the Newton's third law that's happening there. Do F applied have friction constitute? Yes, it does. So let me kind of fill this out for you guys, because we kind of already observed this. So acceleration is 0 meters per second squared, because no motion. And these right here are equal in magnitude but opposite direction. So that's how you answer that part. So definitely want to copy that down. And then the next part, the answer is yes, because equal and opposite forces. When no movement. Okay, so that's the beginning of the lab. Then it says clear the scenario using the button at the bottom. Now gradually increase the applied force until it starts to move. At approximate value of applied force is blocked. So that's what I want you guys to do. I went too high. I went from 250 to 500 to start moving. So I want you to slowly do it. You kind of see that we have to at least, get to like 200 or 250, and then you're going to slowly increase. So I'm going to have you guys do that because, you need to do stuff. And then describe what happens to the frictional force when it begins moving. I'll have you guys write that down.
Mr. Motion, can you put the thing you had back?
Sure. I'll undo. Here we go. Let me readjust it. There you go.
Thank you.
Yep. So again, I'm going to have you guys go in breakout rooms, and I'll probably do groups of 3 this time. So do 4 groups of 3. And you guys could, someone in the room could share his or her screen and kind of just slowly increase the applied force. You could slowly increase the applied force by using this button if you like. So first I have to clear. Why is it not clearing? And let me move. Well, okay, clear. So yeah, you're going to slowly increase this. Then you see some motion. So I'm going to have you guys kind of do that. And so you guys can just click on the link on the, so you guys can access actually, maybe what I'll do is maybe I'll just email this to everybody. That'll be easier. You could open up the file in Schoology too. You do have the file, or you could try typing it in. A little pain to type it in, but you could. But I'll just email everyone the link so you can just click on it. So you guys are going to do these last 2 paragraphs here. You're going to make some observations about what happens when you gradually increase the applied force. Describe what's happening. I'll kind of check and see how that's going. Then you're going to click on the friction tab up top, and you're going to play with that one. And kind of follow the instructions here. And I'd say probably in about 15 minutes, let's check and see how it's going. And then we could probably talk about kinetic friction after that. But we do have this whole week, so we do. There's only 6 pages, so like, maybe we get as far as like the middle of page 2, perhaps. Sorry. Yeah, maybe we get as far as up to here today. So I want you guys to do the last 2 paragraphs of page 1 and go through the first half of page 2, but stop at kinetic friction. Let's check in about 15 minutes or so, so we get close to 1 o'clock. So we'll say 12:55. Let's check in and see if there are any questions. I'm going to kind of go through it myself too. But of course, call me over into your group if you're stuck. And then we're going to do some more practice problems for the last 30 minutes on the same stuff here. Tomorrow, I'd like to do the kinetic and static friction bit. And then Thursday, I think would be a good time to do the assessment on all this stuff. That's what you'll turn in. And of course, we'll keep doing other stuff as well throughout the week. So, okay, let's do this. So is everyone clear what I want you guys to do again? Again, you'll stay on the same thing, force graphs. I'll email you the link again. You'll click on force graphs after I email the link. And you'll just go through these last 2 paragraphs. Then you follow the instructions here, click on the friction tab, do what they want you to do, make your observations, try and make predictions if you can, and you'll stop at kinetic friction. So let me actually do that first. Let's see here. Just copy his email addresses. Okay, just email the link. So check your school emails, or you can just open the file in Schoology, or just type it in, I don't care. Stop sharing my screen. And again, you guys are in the bottom, the last 2 paragraphs on page 1 of the lab, and then the first half or so to the page 2 until you get to kinetic friction. We got 12 people, that's great. I could probably stop